So far, we have looked at very general forms of the maximization problem. One useful thing, however, is that when one looks at maximization problems within the context of economics, the problems have a specific structure that allows the solutions to have a form that has a lot of economic intuition. So what we're going to do for the next few minutes is add this economic structure into the problem to bring out that economic intuition. Let's take a look at what this additional structure looks like. Remember that the maximization problem that we have been studying so far looks like this. Maximize a function t of x over the level x of the action that you can take over its entire domain from minus infinity to plus infinity. The additional economic structure that we're going to impose has three key properties. The first one is this one, which states that the objective function t of x can always be written or can always be split into two components, a benefit function and a cost function. The idea is extremely simple and very intuitive, which is that every time you take an action x is going to generate a benefit and it is going to generate a cost, and that the total payoff for the economic actor, a consumer, a firm, whoever it is, of taking the action is going to be the total benefits at level x minus the total costs at level x, and that adds to the total payoff t of x. I want to give you a couple of examples to convince you that this structure is really at the core of many economic examples of interest, and I will actually argue to most of the economic applications that we're going to do in this course. So consider first an example of a firm. In this firm produces some sort of product, and the level x just denotes how much to produce. The benefit is just the revenue of selling x units. The cost is just the cost of producing x units, basically the cost of production, and t of x is equal to the profit of selling those x units, which is going to be just the revenue of x minus the cost of x. Minus the cost of x, which has the structure benefit of x minus cost of x that is assumed here. Now consider another prototypical problem that we're going to encounter time and time again in this course, which is the problem of a consumer that has to decide how many units of a good to buy in a particular market. And let's say, for example, how many units of computing power to buy, how big a computer to buy. In this case, x is the size of the computer, how many units of computing he's buying, and think of x equals 0 as no computer, and b of x is going to be the benefit for the consumer, the utility of usage for that level of computing measured in dollars. C of x is the cost or the market price of that amount of computing, again measured in dollars, and you can think of t of x as the net utility for the consumer of buying x, again given by the benefit minus the cost and measured in dollars. So once more we see that the problem has a very natural structure that divides the total well-being of the agent that the agent is trying to maximize into a benefit minus a cost, just as is assumed in the structure that we have imposed. The second assumption or a structure that we're going to impose is very simple. It just says that the action has always to be non-negative. In other words, the level of the action x cannot take a negative value. Normally, if x is equal to 0, this is interpreted as take no action, and then as x increases, that is interpreted as take more of the action. Now, this should be fairly intuitive why this assumption is part of many economic problems, given the previous two examples. A firm cannot produce a negative number. A consumer cannot buy a negative level of computing. The smallest action that they can take in both cases is 0. Now, the third assumption is perhaps the most valuable of all from a mathematical point of view, but also the less intuitive. So let's take some time thinking about it. First, let me just describe it to you. Graphically, what it requires is that the function t, which of course is given by the sum of a benefit minus the cost, but that the function t over the domain of the function that is relevant, which is x is greater or equal than 0, be strictly concave. And that basically says that somehow it looks like an inverted ball. Think of this as a ball, think of the water being there, and the ball is inverted because it's facing down. If you care about a precise mathematical definition, it means for a differentiable function that t prima, the second derivative, t double prima at x is less than 0 for all x greater or equal than 0. Now, you may be wondering, why in God's name does this total benefit function t of x is strictly concave in many economic problems? What does the economy has to do with an inverse ball or with the second derivative? Bear with me a second. It's actually pretty intuitive once you see what's going on. Remember that by the first property of the structure that we have imposed, the net payoff function t of x is equal to a benefit function minus a cost function. Now let's look at each of them in turn, the benefit and the cost. It turns out that in many economic problems, the benefit function looks like this. So if this is x and this is 0, it has a shape that looks like this, approximately. The key properties is that the derivative is greater than 0 and the second derivative is less than 0. In other words, every additional unit of x that the individual x gets or does provides some additional benefit, but at an ever decreasing rate because the second derivative is less than 0. Now, many of these economic problems also have the following cost function, something that looks like this. Now, the key properties here, remember this is x, this is the cost function, is that c prima of x is greater than 0 and c double prima of x is also greater than 0. The key idea here is that every additional unit that gets done increases the cost, and that every unit increases the cost at an increasingly rate, so by more than the previous unit increase the cost. So for example here, the first unit increased the cost by this much, but the second unit increased the cost by a little bit more, the third unit by a little bit more, etc. That comes from the properties of the second derivative. Now look at what happens. Suppose that you are in a situation in which the natural economic structure has benefits and cost functions that look like this, and in particular, it is the case that the second derivative of the benefit function is less or equal than 0, the second derivative of the cost function is greater or equal than 0, and it is the case that not both of them are 0. So either this one is strictly less than 0, or this one is greater than 0, or both do not hold with equality. If that is the case, notice what happens. We know that that strict concavity requires the second derivative to be less than 0. But we know that the second derivative is going to be the sum of the second derivatives of b and c because of the additive structure of the objective function. But we know that the second derivative is going to be less or equal than 0 by this assumption. We know that the second derivative of the cost is going to be greater or equal than 0 by this assumption, but there is a negative sign there. So that means, given that not both of them are 0, this is less than 0, i.e., it is strictly concave.